Just when you thought integration couldn't get more fun, we throw in u-substitution. I really like u-substitution. It just really expands the number of problems that you can solve, and I think that's pretty cool. Let's look at this one, the integral of the square root of x minus 2. Using the power rule, I wouldn't be able to solve this necessarily, but I can solve it now with u-substitution. Here's a hint. Anytime there's something under a square root, that's usually going to be your u. So I'm going to let u equal x minus 2, and then you take the derivative of both sides. And so du, and then you take the derivative of the right side with respect to x, that'll just be 1 dx. And now I can rewrite my integral. So this became u, and dx became du. And now this is something that I can integrate. This is u to the 1/2. And so I know that is add 1, divide by it. I can clean that up a little bit. And the most important thing to remember is to go back and plug in what your definition for u was. Can't leave your final answer in terms of u. So this was 2/3. We let u equal x minus 2. And that's to the 3/2 plus c. Kind of cool. Let's do another one. Now I could solve this one. I've got x times x squared plus 2 raised to the 6th power. I could solve that by completely expanding x squared plus 2 to the 6th. So that's like foiling 6 times. I don't want to do that. I want to find a shortcut. And my shortcut can be solving or letting this equal u. Whenever you've got a function inside another function, that's your indicator, that's your red light that you can set that equal to u. And so I'm going to let u equal x squared plus 2. When I take the derivative, du is equal to 2x dx. And I have found with students in the past that this is easier if you'll solve this for dx and then just plug it in to the equation and see what cancels out. That kind of helps you deal with constants a little bit better. So this is the integral of x times, I've made this u now, to the 6th, and dx is du over 2x. By doing this, you see that your x cancels out, and then you've got this 2 in the denominator, so you know you can pull a 1/2 out front of your integral. So this is 1/2 the integral of u to the 6th du. And so I can solve that by the power rule then. Add 1 and divide by it, plus c. So that's u to the 7th over 14 plus c. I can't leave my answer in terms of u, so I have to go back and say, oh yeah, u is x squared plus 2. All that's raised to the 7th over 14 plus c. Done. We can also do this when we have a definite integral. So now I have an upper and a lower limit of integration. To see in this one what I'm going to set u equal to, I'm going to rewrite this part. It's always easier for me to deal with when I see that that is really the cosine of t, and that whole thing is cubed times the sine of t. And remember I said look for that function that's inside of another function. And so I'm going to let u equal the cosine of t. Take the derivative. Du is negative sine t dt. There's a dt there. Solve for dt. dt is du over negative sine t. You can solve for dt, you don't have to. If you see that this is this and you realize you can just put a negative out front, then go for it. You don't have to do this step of solving for dt. It's a good way to make sure you don't miss anything if you get a little bit confused. So I'm going to rewrite this. It's the integral now of u cubed times the sine of t times du over negative sine t. So my sine t's cancel out. I can pull that negative out front. And so I've got the negative integral of u cubed du. Now what have I not done? I haven't dealt with my limits. You have two options. You can integrate, put things back in terms of t, and then use your limits from 0 to pi over 2. That's more work than you have to do. Here's what's really nice. I can change my limits of integration by plugging them into my definition of u. So for example, I'm going to take 0 and plug it in for u. So at 0, that's an a, at 0, u is equal to the cosine of 0. The cosine of 0 is 1. I can do it again. At pi over 2, u is equal to the cosine of pi over 2, which is 0. And so what I've done is I've written my limits in terms of u, which means the 0 became 1, my lower limit became 1, and my upper limit became 0. What this means is I can integrate and evaluate at these new limits without ever going back to x. So you actually save yourself a lot of work. So let's go ahead and integrate. This is negative u to the 4th over 4. I don't worry about the plus c because it's a definite integral, and I don't have to go back to x because I'm going to evaluate now from 1 to 0 for my new limits. So this is negative 0 to the 4th over 4 minus negative u to the 4th over 4. And so that is 1/4. The only reason that I can use these limits and not have to go back to x is because I changed them with my definition of u. If you don't change your limits, then I had to go back in terms of t, and then I could use my old limits. But I highly recommend changing your limits. Just makes your life easier. Let's do one more. The integral of x plus 2 times the square root of x minus 4. Now I told you that if it's under the square root, it's most likely going to be your u. So I'm going to let u equal x minus 4. When I take the derivative of both sides, I get du equals dx. And so when I go to rewrite my integral, I now have the square root of u du. I've got a problem. I've still got an x in my integral. It didn't cancel out whenever I subbed in for du. What do? To get rid of a stubborn x, you go back to your original definition of u. I can solve this for x. I can say that x is equal to u plus 4. I can take this now and get rid of that x. I can sub this in for x and get everything in terms of u. So this is now the integral of x is u plus 4, plus that 2 still hanging on, times the square root of u, I'm going to write that as u to the 1/2, du. Simplify that a little bit, that's the integral of u plus 6 times u to the 1/2. And then going back to my old integration rules, I can distribute this and get something that I can apply the power rule to. So this is the integral of, if that's a 1 right there, 1 plus 1/2, that'll be u to the 3/2, plus 6u to the 1/2 du. And now I can integrate that. For the first term, if I add 1 to 3/2, that'll be 5/2. Divide by it, plus 6u to the 1/2 plus 1 is u to the 3/2, divide by it. There's no limits of integration, so I need my plus c. Let's simplify my fractions. So that's 2/5 u to the 5 over 2 plus 2/3 times 6 u to the 3 over 2 plus c. That'll cancel, that'll be 2 times 2, that's going to be 4. So I'm going to rewrite that, and I'm going to sub in x minus 4 was what u was equal to. And so that becomes, final answer, 2/5 u was x minus 4 to the 5 over 2 plus that fraction simplified to 4. U is still x minus 4 to the 3 over 2 plus c. You should be really proud of that answer. You can integrate really complicated things now. That's pretty cool.